cooperation is by definition an interdependent phenomenon, right? If I cooperate with you, it also means that you are cooperating with me. Trade relations. Trade involves interdependency, even if you're selling someone, like whether the other party actually pays makes you dependent on the other party. So the strategic trade theory, for instance. So several things in international relations are interdependent. For example, military pacts. This is a paper on military pacts or war. So, for example, in this paper, they are looking at international military pacts, and they say our aim here is to model the network of alliances in such a way as to capture the effects of covariates and account for the complex dependencies inherent in the network. Regression analysis, due to its foundational assumption of conditional independence, cannot be used to analyze alliance decisions specifically and interdependent decisions generally. I think this sentence summarizes really the foundation of network analysis. So it is true, because like imagine like why does Sweden want to become a part of NATO? Because it perceives a threat from another country. Why during the Cold War we have the NATO and the Warsaw Pact? Because both parties see each other as a threat. So it's not like a random decision whether France is a member of NATO and US is also a member of NATO is not just independent of, military pacts between the USSR and its allies. So by nature it's interdependent, right? So this is an example of how alliance decisions, and they say we demonstrate how alliance decisions are interdependent, and they criticize regression analysis, etc., etc. So alliances can be conceived as constituting a network where alliance formation is inherently an interdependent process. This is an example of how you can apply this interdependency network here. States are nodes, and edge is military alliance, right? So the presence of a military alliance would be represented by edge formation between state A and state B. The absence would basically communicate no military alliance. So if you're interested, you can basically check this. It's a super cool paper with cool graphs like this. Anyways, and ERGMs. Another example is from American politics. So this is, as the title suggests, looks at legislative collaboration. The Senate Press Events Network. I actually haven't read this piece, so let's look at the abstract together. We introduced participation in joint press events held by US senators as records of collaboration. So by this sentence, we understand that senators are nodes, and basically participating in the same press events would basically translate as an edge. An edge represents participation in the same press event. And this measure captures intentional relationships between legislators along the full timeline of collaboration. So again, collaboration is by definition a relational thing. You cannot collaborate with the other person without the other person is collaborating with you. That's just, two-way. And they show that there's a substantial community structure underlying press events networks that goes beyond political party affiliation, and that press event collaboration predicts overlap in roll call voting. It's another example from American politics. This is a very cool example, actually. I find it very cool because I like historical data. And this one is about the Paris Commune in 1871. It's a very original piece, actually. It's a very, there's also a book about this. So what they look at is insurgency in the Paris Commune of 1871. And the argument is that disaggregating relational data into individual level counts of social ties obscures the crucial issues of network structure and multiplexity. So I analyzed data on insurgency in the Paris Commune and show that organizational networks and pre-existing informal networks interacted in the mobilization process, even in the final moments of the insurrection. So network autocorrelation models reveal that enlistment patterns in the Paris National Guard created organizational linkages among residential areas that contributed to solidarity in the insurgent effort, etc., etc. So they're again using a network model. Here nodes are insurgents, right? And apparently they're trying to look at interpersonal ties to predict mobilization, okay? So that has several applications. I hope that just gives you an idea of like what relational data looks like. And this is starkly different from this regression analysis where you would observe something that is completely independent from something else. So each observations are by definition relational in network analysis, like cooperation, collaboration, war, friendship, love, something like marriages, trade, all these things involve two parties at least. So if you don't have any relational data, you cannot use network analysis. Just like it just violates the underlying assumption. Like other techniques would be more appropriate. Okay. All right. What are we doing today? So today we are looking at share the screen. We are looking at my dissertation data, actually, part of it, not all of it. So this is about insurgency as well. We are looking at revolutionary groups that are trying to overthrow an authoritarian regime. And specifically, we're using historical data. I had collected data on revolutionary groups in the Ottoman Empire between 1895 and 1908, which is the time of the second constitutional revolution, and also France under the Bourbon monarchy, which is the monarchy that was founded right after the fall of the Napoleonic Empire in Europe, and like lasted until the 1830 revolution. Today, I'm going to share you data for 2 specific years from the Ottoman data set. What I try to do in that paper is, I'm trying to look at coalition formation. Okay. So research question is as follows, and I'm doing this exercise just for you to see how you can basically use network analysis to study some social phenomena. So we've seen coalitions in our everyday lives, especially if you're from Turkey, you will be exposed to many coalition news about the opposition parties, for example, right? So these opposition parties, speaking of the Turkish example, have different ideologies, they have different worldviews, and yet they sat on the same table and they basically produce a, entente paperwork. You can see many coalitions around the world across time that have different ideologies. Like, for example, Khomeini collaborated with Iranian left wing, which actually doesn't come as straightforward, right? Like, why does Khomeini cooperate, or why does the left wing cooperate with Khomeini? But they did. However, if you look at left-wing political parties in almost any country, they're not united. That's the other puzzles. Because, like, just because they are both left-wing doesn't mean that they're going to cooperate. And if you look at the history of Marxism, like the very reason why you have something called social democracy is precisely because of the fracture within Orthodox Marxists, right? Why? Because Orthodox Marxists think that they shouldn't be collaborating with the democratic regime. And social, what came to be called social democracy, think that they should play the rules by the game, you know, try to win power and, you know, improve, by coming to power, improve living standards of working class. Like that's the same ideology with different strategies, okay? So the research question is, under what conditions do coalitions form, or when they have similar or dissimilar ideologies? So what explains coalition formation? And the argument I'll be making, actually, I should show this part, which would make more sense. It will open at some point. Well, if not, I can actually do this. Like in this paper, I try to explain two different things: what explains coalition, the form of coalition, and also what explains coalition formation. Anyways, the argument is coalitions form for both strategic and ideological reasons, but strategically unified coalitions are more likely to take collective action than otherwise. So we're going to basically be looking at the first part of this argument. Coalitions for both reasons, but strategically unified coalitions are likely to take collective action. And I think there's another point with this argument which doesn't appear here. Coalitions are more likely to form when partners harmonize their strategies and sideline or settle their ideological differences. So what does this sentence mean for our purposes? So the first part suggests that, like, this harmonization, strategic similarity is a necessity, is a necessary condition. According to this argument, we're going to test this, okay? And the second part says partners should either, you know, set aside all their ideological differences, or they should settle them, right? Like, we no longer have a problem of secularization. We've settled it. Now we can move on and we can work together. Or we have this problem about secularization, but we're going to attend to it later. We have more pressing issues right now. Let's work together, okay? But the idea is that ideological harmony within the coalition is not a necessary condition, and it's not a sufficient condition either, because you have several ideologically similar parties that enter a coalition and cannot get it work for them. So I'm going to share with you a link from which you can look at the data. How do I share? Chat. Is everybody linked to Zoom? How am I going to share this Google Drive link?
Chats.
I did share it in the chat, but shall I email it to you and then?
Oh, no, I will just send a WhatsApp. We have our own secret communication.
Anyway, so here the unit of analysis is.
The whole thing it comes in also just like copy and paste.
Yeah. In this study, the group, the unit of analysis is a group, a revolutionary group. Okay, could have been individual insurgents as well, like the good study. But in my case, like it was horribly difficult to find the reliable data on people. So I use group level data. So what are nodes? Nodes are groups. So what is an edge? Edge basically is coalition. So how do you know there is coalition? What are the indicators? Like, what do I say? I mean, what should I see in the data to say that there is an edge between some group A and some group B? And like I list a bunch of indicators over here somewhere. I actually have all the code written in R Markdown, and I have these indicators written there as well. But since I should be coding along with you, I won't be sharing the R Markdown until the end. So data, blah, blah, blah. Edge. Getting there. So the dependent variable, voila. Okay, indicators include cooperation on sponsoring some bill, generating verbal, written anti-regime propaganda regarding monarchy, policies, plotting a coup, mobilizing citizens through secret meeting, protests, and uprising. So basically this means, like if I read in some source, historical source, group A and B plotting a coup together, I will say that there will be an edge between them. Or if they somehow publish an anti-regime newspaper together, which is a very popular way of challenging the regime at the time, I will be constructing an edge. So the absence of an edge means they haven't done any of these things. So even if they communicate with one another, that doesn't translate into coalition. Does that make sense? So that is the dependent variable. Now let's go to R. Oh, before that, what are the independent variables? I'm sorry, forgot about this. They are a bunch. I have a table about that. We're not going to go over all of them. But since we are looking at the Ottoman data set, we would like to know what these variables are, because you will find them in your data set. For instance, state type. It's an issue that revolutionaries debate, and it refers to the nature of the state to build after transition. What shall we do once we overthrow the Sultan? Shall we establish another constitutional monarchy, or is it going to be an independent nation state without a Sultan? It's a huge question about statehood. Society type. So how will be the nature, the society after the transition? Is it going to remain an imperial society that is multicultural, all ethnicities and religious groups, blah, blah, Ottomanism, or something called Turkish nationalism, but people do not assimilate one another? Or is it going to be an assimilationist Turkish nationalism or some other ethnic nationalism? Okay. Another question, which these two are ideological issues because they basically pertain to like the ideal state of state and society back then. If you read, debates about revolutionaries, so they basically debate statehood and societyhood, and the rest are strategic. So how are we going to overthrow the government? Are we going to do a coup, a revolution? Is it going to be a non-revolutionary change with society basically gaining awareness and overthrowing the Sultan by itself over time? Are we going to use violence, terrorist attacks against our own army, for example, or citizens in order to destabilize the regime? Are we going to seek foreign assistance? Here, foreign assistance refers to European great powers. And if you're familiar with the Ottoman history back then, like the great powers are trying to basically disunite the Ottoman Empire. And since these are revolutionaries that are patriots, they debate about it. So should we seek the help of these great powers because they want to disintegrate us? Or is it okay up until we overthrow the Sultan and then we're going to take care of them after? And the other question is, shall we use religious propaganda to mobilize people? This is not about the separation of states or, politics. This is more about, shall we use religious propaganda or not to mobilize people? And some people are secular, others not. And so there's a debate as to whether religion should be tactically used to mobilize people. And finally, shall we cooperate with secessionist groups, secessionists referring to back then Christian minorities that are trying to build their own nation state, like Armenians or something. And that's a huge debate, and some think that basically it is acceptable because they are part of the empire as well. And others think that this is basically unacceptable because their purpose is to disintegrate the empire. So there are huge problems. So going back to our data sets, let's go to R. All right. So let us start by loading the data. First, set the working directory. So I put my files under this. So I'm gonna, oh, you don't see it. Okay. So you go to session, set working directory, choose directory. Wherever you downloaded the files, you click on it. For me, it was this. For you, it might be something else. Please find that folder and hit open. Oops. Now we're going to read in data sets. Should I wait or are you good?
Maybe like one. So
okay, sure.
Yeah.
Okay.
So. Who raise your hand?
Shall I show you again? Oh, okay. So what's the name of the files? Files. So we can proceed to reading in files. I'm going to start with the edge data. There are two related files. So I'm going to call it edges 96. You can call it anything, but you should just know that, you should just know what you name. Because months after you actually run the analysis, like, stupid object names like my favorite network or something, like doesn't gonna ring a bell. So I think it should be called 96.CSV for everyone. Please set strings as factors to false. And there also is a header in your files. We will be doing the exact same thing for 97. Because I'm lazy, I copy and paste and change numbers. You can totally do the same. Please do not forget to say header equals true because we have a header. I'm sorry, maybe for this one we don't have one. But for the other one, definitely we have one. And strings as factor as false, because especially in the next file where we will be loading nodal attributes, you will have lots of different kind of variables that shouldn't be appearing as factors and remain as strings. Okay, you guys know the difference between strings and factors? String is a character variable and factor is, okay, I'll shut up.
They actually do. They're just too tired.
No, at this point, I totally understand. Like, I hear you guys.
I hope that they do.
Now, the other file is node attributes. Node attributes. I'm going to call it this way, but read CSV. Node. What is it called? Node. CSV. Right. Now we have the data in. So if you want to take a look at what these objects are, like this is an edge list. Actually, now that you said it, this should be false. This should be false as well because there's no header. Let's rerun it. Now it makes sense. Okay, so this is an edge list. These letters stand for different groups. These are abbreviations for different revolutionary groups. What this means, there's an edge between this group called IT and AC. And there's another edge between IT and CUP Istanbul, and so on. If you look at the other data sets, you must make sure that you have V1 and V2 as the column names and not IT by changing header equals false. And the last one is a bunch of attributes, which basically are the variables that I just introduced to you. cooperation with great powers, cooperation with secessionists, secularization, regime change, society type, and state type. Most of these are categorical variables. I had some other numeric variables, but I left them out, like financial sources. There's also in the original analysis, the original analysis is a temporal analysis, guys, not just an ERGM. ERGM is a snapshot of network at a given time, T1, T2, T4, whatever. So we're going to look at type formation in 2 different years, 1896 and 1987. But in the analysis, I look at how these factors change over time. And the network from last year also affects the network last year. So temporal analysis is not what we will be doing today, okay? And therefore, you might see that some variables do not have sufficient variations, but over time there is variation. Okay, it's just a snapshot of, groups' preferences for every year. So what this line says, so this group called AC is against cooperation, 0 referring to against, and 1 for. Cooperation with great powers, it's okay to cooperate with secessionists, and it thinks that they should use religious propaganda to mobilize people, although they themselves are not, they are secular. And they think that the regime should be changed with a revolution. And they believe in Turkish nationalism, and they want a constitutional monarchy, a constitution and the sultan, as opposed to the nation state with, popular sovereignty. And you can read the rest if you're interested. So let's basically continue. Now we should construct our graphs, networks, but before doing so, we should load our packages. Everything's about packages. So if you haven't downloaded iGraph, please do so. You can install packages from install packages over here, which you don't see, but like in this panel upward, you will find install. And here you're gonna hit iGraph. Okay. Since I already have the file, and you should basically spell it correctly. I won't be doing so, but you should install it. And after you install it, you should also call the library, okay? Because this is going to install, but not call the library. All right, we're gonna define, construct our networks using iGraph because it's easier to use than the network package, which did not exist when I was writing my dissertation. So what we shall do, first step, is save your edge list as a matrix. Basically this, IT with this guy, IT with this guy, this is our edge list. Let's save it. The name of the object was E96, and it's going to be save as matrix E96. Okay, now it should be a matrix. Right. We will do the same for the other edge list from 97. Okay. If you skip the step, it won't work. iGraph wants a matrix. Okay. Construct networks using iGraph. So I'm going to call it Net96. So iGraph has this beautiful function, which is graph from, oops, what's going on? From edge list. I think something's happening with them. Graph from edgeless. Something is corrupt. Shall I restart my arc? Can you bear with me for a second? All right. Start over. Reading data sets. Library diagram. Matrices. And graph from edge list. All right. So we will be using this object, and it also asks us whether the network should be directed, to which you're going to say false, because cooperation doesn't have, theoretically speaking, a direction. If I cooperate with you, you cooperate with me. Okay. But you don't need to write this in particular because the default is directed equals false. We're going to do the same thing for the other network. Now we have two networks. Okay. Just to make sure that you have the network, you can simply plot them and see how they look like. They should look like this. Ta-da. These are your revolutionary groups. And notice this is a small data set, relatively small data set, because like most things in socio-political life are like this. You cannot have 1,000 different revolutionary groups in a state, right? Like it's just unreal. You can, if you're running an analysis at the individual level, that might change, of course, like you can talk about thousands, millions, but in this case, like we are talking about groups, how many groups could you possibly have? So it's going to be a narrower data set, all right? But the strength of network analysis lies in its ability to accommodate small and large and middle-sized data sets. So this is considered to be a small data set, but we could basically run an ERGM on a data set of 1,000. If you have a 1,000,000 node data set, don't try to run ERGM. It's not going to work. Then we can talk about how basically you handle this after this exercise. So let's look at the other network as well. Did it run? Notice this graph is disconnected. So there's a pair that has nothing to do with the rest of the people. This is called a disconnected graph. The other one was connected. Basically, it's just one giant component. This has two components, right? Revision from this morning. And some people are very well connected, others not. Some people have just one link, others are very central, etc. So what drives these decisions of alliance? So they seem to be very similar, which is to show you that there are differences between these. I'm going to do a vertex count. It's going to return 16 or 96 and the same number for 97. But you will see in a second that these groups are different. It's not the same 16 group. Because what really happens historically is that some groups exist in 1 year, then they disband, and then something else emerges. This is basically just like current Turkish politics. You have a party, and then it disintegrates, fractures into something else, and then there's a novel party, then there's another movement, and then they merge, etc., etc. So this is the same thing, like a century ago. So, are you able to follow this part? Great, let's assign our nodal attributes. Node attributes. So again, what do we call node attributes? This is what data scientists or machine learning people call feature for observations. We call it node attributes in this data set that basically refers to, where's that? I should have made this. This is basically all these variables, because we are basically assigning each group its preferences on these ideological issues. What do they think on this issue? Do they think similarly? Do they have the same view on how society should be organized? And if they do so, does it lead to cooperation? Or do people who have the same exact view on society type, nevertheless, happen to work with people who have different viewpoints on this issue? So that's the thing that we are testing here, right? Like, does ideological similarity or strategic similarity lead to alliance formation? All right, so let's assign them. For this, we should first make sure that, notice you have about 30 groups over here. And in our network, we have 16 nodes. Like I said before, this was a temporal analysis. Some of the nodes that appear in this list do not exist in the network that I give you. So you cannot just assign them, because there will be a mismatch. You will try to assign 30, properties on 16 nodes, and R is going to run into an error. So first, we basically subset the nodes that exist in this year. So, set a node list for each network. Okay. So we're gonna say nodes in 96. So this is how graph works. This means vertices of network 96, and you assign them a property using this. If you check this list, it's going to be a vector of the nodes. We are doing this to prove you that these networks are different. There are different groups. Oh, also I should call the object. These groups are different. That's why you want to make sure that you subset the right section, okay? Even though the number of nodes equals 16 in both of them. These are different. So we want to filter the ones that exist. And I'm going to call it filtered 96, which is, this is done for subsetting. It's the same. Go to node attributes object such that in node attribute, names are those that are into node 96. Let me go over the structure again. So this is saying I'm going to subset from this node list, large data set that have 30 nodes, the ones that match with the node list that I constructed for the network 96. So this in means like in those matched ones within the large network. And if you check what this looks like, it only contains the ones that you have for the network 96 and all the preferences that comes with those nodes. We will be doing the same thing for 97. Okay, so I'm going to create something called filtered 97. You can call it something else, but it just helps me remember what I've done before. So within node attributes, find the names and make sure that they are the ones that are in node 97. This is what this line of code means. Now, if you look at it, it's going to be different nodes, and their preferences. Now we assign. Assign node attributes. Here we will be writing a bit. Any questions? So
in the 96.
right.
Okay.
So because we had a large data set like this, 30 different things, and for 96 and 97, we had BBCD up until whatever, and 16 in total. But then we had alpha data something up until whatever, and 16. So you're gonna find here A, B, C, D, and import those references. And do the same for this. Just identify which are which and only import them, because otherwise it won't work. And try this work. Now we will be typing a little. Okay. So the way we assign node attributes in iGraph is vertices of network 96. And if you just hit this, it's going to print you a list of all the vertices. Now, what you want to do is to assign them a property, just like in every data set. For instance, in here, we have a data set called node attribute. Right. So if you want to call a particular column, you're going to refer to that column with a $sign, right? So that's the same idea. So here you're going to create something new, and we're going to start with cooperation with secessionists. So it's going to come from this filtered 96 data set. Just to make our lives easier, I'm going to ask for column names of filtered 96 and copy and paste because it's not the same, okay? So I'm going to write the full name over here though. So cooperation with secessionists is how it was stored in this data set. Okay. Now, if you hit this to see if you actually did things correctly, you will see an output with missing data represented as 9. Now we're going to assign the other ones. Next, we have cooperation with great powers with GP. And it's going to come from this filtered 96 data set. And it's stored as co-op underscore GP. It's also stored as ones and zeros. Now we move on to the next reference. We can move on to, bless you. So just to note, these are ideologies. These are strategies. So from this filtered thing, secularization. I like to abbreviate everything. As you can see, it's a bunch of, character variables. These are categorical variables that are nominal by definition, because you cannot say tactic secular is greater or smaller than tactic something else. There's no such thing. Okay. And hang in there. We just have a few left. All right, what do we have missing? Society type. Society type. That is talk type. Oh, that's actually, I'm sorry, I'm very tired myself. This is an ideology. This is a strategy. This is a strategy as well. Voila. Let us finish with state and society types or ideologies. Rest is about how to overthrow the Sultan, so it's all about ways of doing it. We have, what else did we have left? I need regime change. All right. We have successfully assigned our nodal attributes to the first network. Now we have to do the same thing again for the other network. A pain in the ass. Like you shouldn't be working on opinion dynamics. People have ideas about everything. Okay, but fortunately we can simply copy and paste and change numbers. For that's 97. What name?
There's also one for name.
Oh, name is for the names of the groups, because if you don't, each group will appear as 1, 2, 3, 4, something, and you won't know which node is which group. I mean, for this analysis, it might not be fatal to oh, actually it is fatal because we are using this, we are doing this filtering thing based on names. So we must have names. So I change all 6 into 7s. No, I haven't. All right, do you guys see any 6? No. All right, now we have done the exact same thing for network 97. Now we are moving to the modeling part. Actually, let me do this. ERGMs. So first, load libraries. You want to install a bunch of packages from here. Oh, we don't see the packages thing. Oh, I see. This is what I should change. Okay, for over here, packages, you hit packages, install. You're gonna install 4 things: statnet, comma, network, comma, ERGM, and intergraph. So the reason why we need all these packages is, fortunately, the ERGM analysis doesn't work with iGraph. You have to convert your iGraph objects into networks, and we will be using intergraph to convert your objects into another class called network. Okay. We could have done without iGraph, but it's the latest package. It's easier to use. Trust me, if you work with base R, it's much more complicated. You first establish the node set, you say there's an edge, and then it's awfully complicated. So iGraph is better. So you hit install after that. I don't want to restart. It's gonna start downloading all these things. And we're gonna call the library stuff now. You have an error message for me with ERGM because there's a clash between iGraph and network. And so if you run network, iGraph will be masked and vice versa. But maybe it won't give you give an error message for you guys, but it's not that important anyway. So step one, convert your network objects into a network object instead of an iGraph object. So if you don't believe me, you can ask what's the class of, what was it, Net 96, right? It's gonna say iGraph. We don't wanna have iGraph. So we're gonna overwrite this as using the iGraph package, and it's gonna be as network. And you overwrite function. What does it say? As network. Now it works. Make sure that you also read the libraries. Now, if you want to check, you can rerun the function class. What's the class of this network object? If it says network, you're good to go. Otherwise, you want to actually redo the step. We'll be doing the exact same thing for the other network. Okay. Now let's check if the class is net 97. It's also a network. Congratulations, you finished all the boring parts necessary to modeling. Now you're gonna have even worse parts. We'll be running the model. It's just that running the model is fun, but you will see that it's actually difficult to interpret and choose among models. And let's work with this. Should I wait 1 minute or 2 minutes before we? Organ. People, good news is the sentence structure for running an exponential random graph model is the same as any model in R. So if you were to run a linear regression, you would say LM dependence variable tilde my IV1 plus IV1 plus IV2 and specify your data, right? And you would be storing it as an object to refer to it later. We will be doing the exact same thing. So we're going to start with an estimation. 1 for network 96. That's what I call it. You may call it something else. Because the problem is when I was doing this, I had to run like dozens of estimations in order to choose the best model. And you will see actually how it works in a second. So you may want to go back to the estimation model number something. So you want to know which one is actually which one. And you don't have the many dependency terms in this model, but when I was doing this, it would take me several hours to have an output for one. Then you would do the same again, wait several hours, etc. So you want to have the estimations ready. So the sentence for this is ERGM. Okay. Now, what you are trying to predict is your network. Okay. In this case, the first one, tilde. You write the term edges. It's like your intercept in your regression model. Okay. Then you will start introducing your nodal attributes one by one. Okay. So you may start by actually the simplest one, which is just the edges. Does it say ERGM? Didn't work. Stop next. Oh.
It says you might have to update those packages. Yes. Upgrade some of your packages.
I have to upgrade some of my packages.
Which was .NET.com.
This just doesn't make sense because this morning I ran this and they were working perfectly fine. So which one doesn't work? ERGM, right? ERGM, reinstall.
It's not about
which one?
.NET.com.
Oh, .NET.
.NET.com. Yes.
I see. Okay. Thank you. No. Thank you.
Install again.
Yep. Cheers. Thank you. No. Oh, I have to. I have to install .NET again, I guess. .NET. Not here.
I guess you have to delete the existing .NET account, like folder from your library folder in R, and you have to reinstall it again. So. Switch the file. Or you can remove packets by using the remove function.
Jesus. Remove packages. Okay, which one should I remove? Sorry, I'm tired. Just how long? Okay. Reload.
Now first, that's a pretty follow point of place. Yes.
Why am I clicking yes?
Yes.
I just click no. What did I say no to? I thought I didn't want to restart R prior to installing.
All things are not going.
Okay. Thank you. Yep. All right. Phew. Thank you. So I'm going to delete this. All right, notice that it runs the maximum likelihood because we don't have any dependency. We don't have anything, it's just edges versus the network. But for anything, you actually want to see the summary. And here, what it says, the edges term is statistically significant and the coefficient is negative. So as the number of nodes on the network increases, we are much less likely to see tie formation. This is what it means. If the coefficient were to be a positive one, then we would be saying as the number of nodes on the network increases, we would be more likely to see tie formation. In plain language, like if the number of groups and the revolutionary groups in that environment increases, there will be fewer cooperation among them. Now we want to know why. Okay, that's what the baseline model says. So here we're trying to look at homophily, right? Along strategic and ideological preferences. So let's create another estimation. So edges, sorry, not this way. The way to use homophily on categorical variables is by using this function called node match. You're matching your nodes based on categorical values. If you actually hit the packages, you will see an explanation for all sorts of functions that you might possibly need based on numeric variables, numeric and directed graphs, categorical directed graphs, etc., etc. You may find all sorts of possibilities, functions for all sorts of possibilities in this network. So let's start with the first one. Let's just see society type. So what I'm doing is, this is saying run ERGM, basically try to explain type formation on this network using edges and homophily along this preference dimension. It's not statistically significant. How do I know that? There's no star. Okay, right? Edges are statistically significant. State type is not statistically significant. What does it mean for us? Like, you don't want to actually find everything to be statistically significant in this case. This is actually quite telling for my purposes, because I say that like ideological similarity doesn't determine coalition formation. And here's proof to you that basically coalition formation does not depend on ideological similarity when it comes to society type. So people, even if they hold different preferences or similar preferences, they do not make their alliance decisions based on what they think on this issue. Okay, this is what it means. I'm not going to run different things, just going to add some other variables. Let's look at the other ideological issue, which was, I think, state type. And let's see everything again. This is not statistically significant either. On this doesn't mean anything, by the way, about the larger realm of ideological preferences. The inference you will be drawing from this output is that in networks similar to this, given this data set of Ottoman revolutionaries in 1896, we don't find any evidence that ideological similarity among these two dimensions drive coalition formation. Again, this is very important because it doesn't mean that ideological similarity doesn't explain coalition formation. It doesn't explain coalition formation for this data set in this time step, okay? And we shall see maybe if we add other variables, it will turn out to be significant, okay? And this inference making, like generalization, holds for every source of every kind of modeling. You cannot say that because you run, I don't know, wages against age and experience, and you don't find experience to be significant, that it's not significant around the world. No, you're using a certain data set collected under certain circumstances, okay? For this data set, you don't find evidence suggesting that experience explains wage. But in another data set, controlling for other things, it might turn out to be an explanatory factor, okay? So let's try with other things. Let's add statistical strategic variables. Node match. And what do we have? We have secularization. And see what happens. So run 3. Well, nothing is statistically significant. It's a very weird network, okay? Can add other strategic preferences. What were they? Regime change. Nothing became significant when you added this variable. Let's add all strategic variables, strategy variables, and see what happens. But normally you should proceed one by one, okay? I'm only doing everything at once because we have another network. Nice, and it's 9:30, okay? All right, cooperation with GP and node match cooperation. There's nothing significant. In part because we forgot to control for missing data. Remember when we were looking at the variation in society type and state type over here? Sorry, not we. Sorry, not this one. Yes, this. It's ones and zeros and nines because there are missing data in everything. And we have missing data for cooperation with great power. So what this is trying to do is to match all these numbers, including 0, 1, and 9. But you should only keep, you only want to keep ones and zeros, okay? So we want to add this. So to do that, you're going to write keep, okay? Equals, which ones should I keep? 0 and 1, right? And we're going to do the same thing for this one. Now you find that the cooperation with secessionists is highly significant. So much so that this coefficient basically totally predicts the absence of an edge. Like if you think differently in this period regarding whether you should be cooperating with a secessionist group, you can, well, that preference definitely explains your decision about coalition formation. So two people who think differently on this issue will not be cooperating. What is also interesting for our purposes is that we would like to introduce some interdependence term. So all these things are preferences. Preferences about society type, preferences about state type, preferences about secularization and regime change, etc., etc. And with this model, we've only looked at whether, having similar views on these dimensions make a statistically significant effect on coalition formation. And we found that ideological similarity does not matter in explaining coalition patterns in this year. And some other strategic preferences don't matter either, except cooperation with secessionists. So this is a very polarized environment when it comes to what you think about the other secessionist group based on this outcome. But you could also think that like certain decisions are tactical, meaning that like if I trust another revolutionary group and that group trusts another revolutionary group, I might be able to trust that other revolutionary group. Basically this idea of transitivity, right? Like this triangle thing. So this guy works with this one. And I trust B, I'm A, and B works with C. So I will be inclined to work with C. This is called transitivity, right? So here we go back to our discussion about degeneracy. So what is this? That's basically a triangle. But if you want to add this and add the term triangle, you're going to bump into degeneracy. Okay. So instead, we will be using this last term, Gaussian weighted exponential something. You can check it. Okay. So it's going to be fixed to some value. What this is doing is for every triangle, additional triangle, it's going to multiply, it's going to have a coefficient, let's say alpha or whatever. Oh, okay. And this is going to downplay additional value of, the marginal value of an additional triangle. And we're going to fix it to 0 here to basically be very conservative. Could have put it, you could have set 2.5. So this is also down valuing, right? But not as much as 0. And we're going to say fixed equals true. Now that you will have added this interdependence term, you will see that you will be running an MCMC algorithm. So it's WASP. WASP 0 fixed. Perfect. All right. Now it's going to take longer. Notice it's running a chain. See? It iterates once, it iterates second, another time. It's already done. This is what I was trying to explain with this Markov chain, right? You're running a simulation and choosing whether the present network configuration is any better than the ones that comes next. If it is, then you basically drop this one and adopt the other one. You're basically improving the likelihood by these percentages. And at some point, it converges. Right? It converged. The model was fit using MCMC, stuff. But we still don't know whether this is a robust model against degeneracy. We will basically see this next, but let's see the output of the model first. GWASP. This is the transitivity term. My friend's friend is my friend kind of thing. These are all homophily terms. Like now that we actually read this, if we were to look at differences across dimensions, we would like to set this to false to look for heterophily. So there's homophily. This is the tendency to work with those similar to you, and this is the tendency to work with those different things. Why would that be meaningful? Like if you're, for instance, heterosexual person, you would like to date another gender. If not, then you would like to date the same gender. So if you were to run a model like this, on dating patterns, for example, note that gender, you may want to look at the effects of heterophily or homophily. If you run homophily, then you will find the propensity to date those who are of the same gender. You set it to false, then it's going to be heterosexual relationships. And for our purposes, it might be interesting as well. Like you may want to know how a particular, let's say, left-wing group considers other left-wing groups. Let's say it doesn't exist in this data set, but it exists in other data sets. Suppose you have group 1, which is the left-wing group. You have another group, another left-wing group that is differentiated on some dimension, I don't know. And if you want to look at heterophily in particular, you would find, and if it is statistically significant, some evidence that this group prefers to work with other groups, but not with the left-wing group because of some fear or some, personal disagreement or leadership issues or some very important ideological difference within left-wing, something like that. So if it is theoretically meaningful for you, you should definitely check this. Not for this case. All right, so in this network, we didn't find any evidence that actually validates the tendency to work with groups that are allies with other groups. Trust is not transitive in this here. That's what the outcome says. Now, one thing, how do I know that this is a good model? This is a better model than this model. Any ideas? How would you choose one model over another in? Yes. AIC and PIC. Archive information criteria. Bayesian input criteria. Yes, you had a question?
Just my summary, like sure yes.
Did you hit this? Okay, I misunderstood the question. I thought like your code didn't show this output at all. I misunderstood the question. Sorry, it's almost 10. So All right, yeah, we don't see that. But we do see actually the ones for the other ones.
Yeah.
Right. Actually, we should be able to see that, but I don't have the other either. But let's first talk about these ones without the interdependency terms. So what I want to have is a very low AIC and BIC criteria, right? Why? What do AIC and BIC do? Are you familiar with these terms, or should we? Okay, so these are two criteria that are heavily used in modeling, because in any kind of modeling almost, and especially maybe not this one, but definitely in regression kind of things, if you add more variables, then your explanatory power will increase. Especially you will see it increasing R-squares or stuff like that. But that doesn't mean that you have a good model. So you want to actually have the smallest, the simplest model possible and explain the most with that simple model. This is called parsimony, right? This is the idea behind modeling. We don't want to have something that predicts every small detail, whether it's going to rain. It depends on several factors. And you might, if you knew every parameter and had values for this, you could predict the weather tomorrow. But it's not going to hold for the weather in, I don't know, London or something, because certain things are different. So we're not interested in exactly predicting what happens in Istanbul on a Friday night or something. So in modeling, we actually want to have a certain viewpoint as to how parameters behave. And therefore, we don't want to add too many variables, right? So these AIC and BIC criteria are used to penalize models for every additional explanatory term you add to your equation. So if these are small, because these are very conservative scores, the smaller the better, okay? And it says here, smaller the better. So if you're ever confused, you will find the note here, R does that for you. So basically, that means if you don't add that additional variable, you will have an information loss. Information loss is measured here. So what do I lose by not adding that term to my equation? So let's compare these ones. In this model where we have society type and all these things, we have the AIC, which is around 165.6, and then results. 162.4. What's the difference between these two models? So this one has the ideological variables and only some of the strategic variables. Here we added all ideological and strategic variables. Okay. And this is not diminished. So maybe adding them all together is not a good idea, right? Based on this. Right? Smaller model is a better one. So you shouldn't be running everything at once. That's what you learn from this. All right. Let's do, let's try to interpret basically the coefficient for WASP. WASP is not statistically significant in this model. So it's not going to work. Let's try with the other network. Let's look at 1897. S1. I'm gonna copy some of these things. Okay. So don't forget to change the network. Here we are only running not even this. Network against the edges, and summary as stuff. The edges are statistically significant, the coefficient is negative, saying that as the number of nodes increases in this network, we are likely to see fewer tie formation. So as there are more revolutionary groups, we expect less cooperation. Okay. Now let's add this transitivity term and see how stuff changes, if any. Notice that it's converged very fast. This is what you would like to see. The other model was prone to degeneracy because you actually want to have the convergence happening at few steps, but we will check diagnostics in a second. So it converged rapidly, and looking at the results, edges are significant, but apparently in this network, WASP is not statistically significant either. If it were, how would we have interpreted the coefficient? This is a question for you. If it were statistically significant, if you had 3 stars, what would you have said about this coefficient? Exactly. It has a positive impact of cooperation, we would have said, and transitivity basically improves, coalition formation in this network, given this data set in that year. Okay. And if my advisor were here, he would have said, in networks comparable to this. Let's add some of the ideological variables. I'm going to copy over. Create another object so that we can choose. All right. So these, according to this output, ideological similarity does not explain coalition formation. That's what we learned. Let's just run strategic variables. By the way, I haven't done this before. I'm also finding out with you because I had the temporal network. I just saw everything, not like looked at particular years, what will happen, etc. So estimation number 3. Okay, in this network, we find a statistically significant result for WASP. Now, how do we interpret this? Finally, some statistically significant. No, very hard for that. Yes. So, this transitivity term explaining cooperation with a partner of a partner turns out to be statistically significant, and it improves the probability of tie formation. So more coalitions are formed because people will trust their partner's partner. But again, what is interesting here is this is highly significant, and basically definitely explains the absence of tie formation among those who think differently on the strategic issues. But on other strategic issues, they don't matter. So the interpretation of this, for example, what people think on whether to cooperate with great powers has no impact, statistically significant impact on decisions to form coalitions, right? It doesn't have any statistics, holding everything else constant. Okay. If you want to play around a bit more, you can take out and add some stuff, etc., etc. But I think we want to talk about diagnostics a little bit. So I'm going to leave that one part to you. Diagnostics. All right. So first, we want to look at MCMC diagnostics. So for this, we are doing this to see whether the graph has degeneracy issues. We want to see how the Monte Carlo chains are mixed, how well they are mixed. Okay, so to do this, you're going to basically run the model results. Since we actually saved it as an object, we are just going to run this. It's going to produce a bunch of things like this. How many iterations it made, the thinning interval, number of chains. You can specify all these variables, by the way. You can see cross correlations, etc., etc. So this might be something that is interesting. Are sample statistics significantly different from the observed? What's the difference? Statistic and p-value associated with it, right? That might be interesting. Autocorrelations. Some variables seem to be highly correlated. So you want to basically leave them out to not to have multicollinearity issues. Actually, not these strategy variables. They don't seem to be highly correlated with one another. So the edges with the west term. All right, so the thing that you would like to look at is this joint p-value and this part. So this is similar to this f-test we have in regression. So does the model make any sense? Is it statistically significant? So what's the joint p-value of this model having all these variables? And the lower is worse. So here we have a large p-value, 0.5 is a large p-value, right? So it's not all that bad. And individual p-values, this is similar to, the test statistics we do for, each regression term. Are you guys familiar with this? For example, X2. So the coefficient that you find in the R output is basically the estimation of E1, right? This is what we observed here in this output. Right, this is your estimation, standard error, and a whole bunch of stuff. And we start with we refer to the individual significance of that coefficient. So this is similar to that. And you want to have them to be high. Where were we? Okay. And yes. This is important. So it also produces certain plots, and the ones over here tell you about how well the MCMC chain is mixed. This is an okay mix. And that mix would look something like that. It doesn't. Here it's mixed. What you would like to see here is like a fuzzy caterpillars, right? Something that makes this well. If you don't, like, you should have something again like this, or, you know, you can discern each line. You don't want to discern lines. It should look like this. And on this side, you basically look at here just two variables. If you go back to the plot, you will see the plot behind the variables as well. This should look as similar as possible to a normal distribution. It shouldn't be skewed. Okay. Let's see how it is for the other ones. Is it well mixed? Oops. What the hell is it? So here it's not perfect, as you can see, but you can say it's okay, but not great. This is somewhat less well mixed than the other ones. So there are certain issues that you may want to consider to improve this model. Maybe not put all of these strategy variables, maybe select some of them. Okay, stuff like this. Or also you may consider adjusting parameters, the size of the MCMC sample in particular. But let's finally look at the goodness of fits. So the goodness of fits is GOF function, and you have the object. It's going to print out a bunch of numbers like this. So how well do I do in predicting the observed network? So in the network, I observe 42 edges. So across my simulations, the least I found was 30. The max was 57. On average, I predicted something like 41.58. This looks okay. Okay. So basically, you want to have your mean observations, predictions to be close to your observations and maybe not have a huge variation, because as you will plot them, you will see that it might go above the box plots. So your predictions should be close to the observed values. You will see them over here, and the associated p-value, this should be high as well. Let's plot this. Let's say G is this and plot G. All right, this is what you obtain when you plot these. It's going to produce three graphs like that, three plots like this. One, minimum geodesic distance for network level. Two, edge-wise shared partners, edge level, and degree for node level. These are standard things that it prints out all the time. So looking at this plot, you can see that we messed up when predicting the degree. This is not a good model for predicting degree. How do we know this? Because this is our predictions, the plot, this thick black line. And these are the box plots, you know, median and, you know, like quartiles over here. What you would like to have ideally is not necessarily going through all these blue dots, because you don't want to be over predictive even exposed to machine learning. It's not something that you would like to do, because you don't want to be that specific to the data. But you don't want to have that either, because it goes above box plot. So here what it's saying is for degree 0, okay, I did an okay job, but for degree 1, I severely over predicted. And for this degree 2, I under predicted, over predicted, under predicted. It's a mess. Okay. Let's see how it's fared for edgewise shared partners. So for these two, we didn't do a good job, okay, but it seems to be acceptable between these, numbers. But when your the number of your shared partners increases, you basically do not do such a good job either, okay? Again, what you would like to see is not maybe that it goes through the middle like this, because here we basically fit the data too well, but not on other things. So you just want your predictions to be within the box plots. In that sense, this is too good. But this one wasn't good. Okay, to wrap things up. So once you run the ERGM, you're going to obtain some outputs like this. Okay. This is going to tell you your estimations for these parameters. And in this particular case, we try to predict what drives coalition formation. And we basically looked at ideological similarity and strategic similarity on different issues. So for this data in that year, we didn't find proof for, like this didn't run anything ideological, but most of the strategic things except this one. Apparently, this is a very thorny issue that polarizes groups, and if they think differently, they're not going to cooperate. We know that. So you're going to try running different models, okay? And you will evaluate them based on two things, AIC, BIC, okay? That's one thing. But you also want to see whether, goodness of fit for one model is better than the other. So how well you're doing in predicting the observed network with this model than with this model. If one is better, then you should definitely choose that model. And once you have chosen the model, you can use it to simulate networks and to run, you maybe make predictions, not in this case, because it's like these guys are dead for over a century. But if you're doing, some analysis with more contemporary data, that might become handy. Like if you're working on military alliances, that might, for instance, help you to predict whether some state A and B will form a military alliance or something. Once you have the output, you should definitely run these diagnostic tests, MCMC diagnostics, and you want to make sure that the model is not degenerate, because ERGMs are great, but they are very prone to degeneracy. Okay, you want to make sure that the chain is mixing well, like that. You want to see a fuzzy caterpillar, not a discernible line. And then you want to see how well you're doing in predicting the observed network. These are the steps that you should be following. Before I shut up, I'm gonna say one last thing. There are other models, okay? This is an intro thing to modeling with networks. The reference paper does a temporal analysis, okay? It's like time series of the network analysis. So this is not something that we will obviously do today. But there are other models like latent space models, and there's also the SNA model. I forgot the non-abbreviated version. But you will find different models, statistical network analysis. And I'm happy to refer to you to these books. I'm gonna share my slides through chat. It contains all sorts of information. What did I just do? Oh. File. Because it also contains voila, the link for the R Markdown. So if you weren't able to keep up and it was a long day already, so you will find over here a link to R Markdown with explanations, link to data, and references for exponential random graph models. Now we can go to bed. All right, thank you, everyone. Shall I just... Shall I just leave the...
I will continue the recording in case one question comes and then it's still not the AIC.
Oh yeah, I forgot that. Let me check with the other one. Hold on. This shouldn't be the case. Still don't get it. With this data, we don't get, I tried with both networks, it doesn't print AIC-BIC when you include GWESP. But when you exclude GWESP, it does. I will have to see whether this is the case with other networks. Let me run some other thing, okay? I think the answer to your question is you must have some AIC and BIC, but I suspect that this has to do with the data because I ran this time series thing and I see AICs and BICs for both periods. I mean, we could try to run with other things, but we have to wait. If that's okay, I'm happy to run. Could be that this is a small part of the data and let me try with this one. Doesn't produce AIC and BIC with this data set. Now that you got me thinking, I'm gonna see the original analysis and see what happens, but I don't know how long it will take. If you did, can you share the solution with me? I'm curious. So I started rerunning everything.
Nobody has